So the subject of the talk is some work that we are finishing with Andrea Guerrieri and Joao Penedones. So we hope to put this paper out next week, early next week, maybe tomorrow, maybe after tomorrow, depends on. We are waiting for a few plots. If those plots are not a disaster that contradict everything I'm saying today, we should put out the paper tomorrow. If so, yeah. So if we don't, it's because there's something unexpected happened. So the plan is to use this S-matrix bootstrap that we have been developing for carving out the space of quantum field theories to see, now that we have been working on it for a few years, if we can apply it to say something about gravity and where could we put theories of quantum gravity using the S-matrix bootstrap, and whether we could see that string theory appears in a special place within the space of theories, or whether it appears in a random place within the space of theories. Okay. So, but before I would like to start. So the plan, what I would propose to do is to start with a simple toy model with an example, which I always like, which is an example, a toy example of understanding the space of holomorphic functions. And then we will generalize this example, and instead of having one holomorphic function S of a single variable, we will go to amplitudes that are functions of two variables, an angle and an energy. But we will see that there is many parallels between quantities that we consider here and quantities that we'll consider on this side. And in the same way that we put bounds on the space of holomorphic functions, we'll be able to put bounds on the space of amplitudes. So that's basically the plan, is to start with a toy example and then move based on that example to the study of amplitudes. So I'll start very, very basic with this example because it allows us to illustrate a couple of things that show up here in this side of the bootstrap, based on some simple questions that we can ask about simple holomorphic functions S of Z that are bounded holomorphic functions. Okay. And so the question I'll start is the following. Suppose I have an holomorphic function that is defined in a unit disk. So this would be the unit disk. And inside this unit disk, I have a function f of z that is holomorphic, no singularities. And that is bounded on the boundary of the unit disk. So here on the boundary of the unit disk, the absolute value of f is smaller or equal than 1 at the boundary of the disk. Okay. And then we ask the question, let me put in a different color. Here, say at the origin, I have f of 0. Let's suppose the function is a real analytic, meaning that the function in the upper half plane is the complex conjugate of in the lower half plane. So the f of 0 is a real number. And we ask, what is the maximum value of f of 0? So let me define f of 0 as some g, and we ask, what's the maximum value of f of 0? Okay. So that's the problem we could ask. And let's solve this problem, this trivial problem. So you might immediately shout the solution, you might know the solution. But even though it's a little bit pedantic, let's solve it in two ways. Let's solve this simple problem. It's a simple mathematical problem. We could give it in some course of complex analysis. But let's solve it in a simple way. And let me solve it in a way that I will call the primal approach or the primal solution. And then we will do a dual solution. Now, the primal solution basically means that you construct examples. You start constructing examples and you try to construct better and better examples of bounded holomorphic functions. And the better is your example, the better will be the value that you get for f of 0. And you try to converge towards the optimal solution that will have the biggest possible f of 0 at the origin. And so you start with some examples. For example, you could try f of z equal z to some power, right? So this would be a phase at the boundary of the disk at absolute when z is a phase. That's definitely bounded. This guy would give me f of 0 equals 0. That's not a very big number. I could try f of z equal 1/2. 1/2 is bounded at the boundary of the disk, and this gives me a better value, f of 0 equal 1/2. I could try f of z equal 1. This gives me f of 0 equal to 1. And now you could think, can I do better than this? I did 0, I did 1/2, I did 1. Can I do better, right? Can I do 2? And I could try 2. And if I don't know complex analysis, I try 2 minus z squared so that it goes down. But then it blows up in the imaginary direction. It doesn't work. So I try minus z to the 4, but then it blows up in some diagonal. And I try, but I cannot do it. So what's happening is that as I am becoming smarter and smarter, so here let me put some n to indicate like my computer time, how smart I am. I start with a bound. So first I guessed 0, then I guessed 1/2, then eventually I guessed 1. Maybe in the middle I tried the function 3/4, whatever. And so it seems to go converge. Maybe I can do better than 1, but 1 is so far the best value I could find. Yeah. Now this idea of approaching what should be the optimal bound by constructing explicitly solutions is what is called the primal solution, the primal approach. Namely, no one, for sure, I know this exists. So this is included. So this is not an exclusion plot, but smaller than these values exist for sure. Above, I'm not sure yet. Maybe I was not clever enough. Maybe my ansatz was not powerful enough, right? Now, let's be even more explicit and think a bit, how would we solve this in a computer? How would we try in a computer to be smarter than 1, right? Well, it's very simple. We would say the function is holomorphic and bounded, so it admits a Taylor expansion, which is convergent inside the unit disk. So in a computer, we would say f of z. We would put in a computer saying it's a sum of some fn z to the n from n equal to 0 up to some maximum number n. It could be that number here, or it could be some other number. Let's put some n hat. Some maximum number n, which is a way of parameterizing my ansatz. And the idea is to take n to be big, like 100 or 200, so that we describe very general functions, right? And then we ask, next step, we make a grid of points, and we make a grid at the boundary of the unit disk, many points. Right? So this defines many points zi in a grid. And then we just ask Mathematica to find maximum, maximize what? F of 0, F0, which is the value at the origin, subject to some conditions. What are these conditions? It's just that absolute value of F at all these points Zi are smaller or equal than 1. So that's how you do it in Mathematica. You just maximize F of 0 with these constraints. Okay? And Mathematica will tell you F of 0 is 0.999999999. So you are probably smart. It's probably 1 and you cannot do better than 1. Okay, so you do this and you find a value also here at 1. You never know. Maybe you need n to be 2 millions to reach the 1. But okay, so far we saw 1. This would be the value that we would get in this primal numerics. Okay, so let's move. And again, I'm assuming there are no questions. If there are questions, please interrupt me. Otherwise, let's solve this problem again, but using what we would call the dual solution.
Pedro, I have a question.
Yeah. Good.
Isn't there some theorem called the Schwarzschild theorem that tells you that the absolute value of this analytic function will always decrease as you go towards the center?
Yeah, no, not exactly. Yeah, that's right. So yeah, I said we could be smart. So if we are smart like you, we know this all this theorem, the maximum modulus principle. So we know functions don't have maxima, right? And therefore, if a function is bounded, must achieve its maxima at the boundary because holomorphic functions don't have maxima.
Right. Okay, all right. Okay.
So we can be smart because it's one function, one variable. What we'll do with amplitudes, it's harder. Okay. So it's better not to be so smart.
Okay. All right.
So but we will derive this result. We will just not derive it in the fastest way, but now we'll derive it. Because now we'll do the dual formulation. So the dual formulation, so at right now, let me just put here in the corner, what we did is we said that the maximum of f of 0 is equal to g. And I don't know what is g, but I know that g is for sure, the maximum is for sure 1. Right? Because 1, we found an example that gives 1. Okay, but now with the dual formulation, we approach it from the other side. So we saw that G is bigger or equal than 1, right? We saw that I can go 1 for sure I can reach, maybe more than 1, but 1 I can reach. And but now we are going to squeeze this, and now here comes the dual bound. And so in the dual solution, what we point out immediately is that f of 0, this value that I want, is the contour integral, right, of the function f of z divided by 2 pi I times any function k of z, provided this contour here is around some small circle, and this function k is 1 over z plus regular. Right? At the origin, it behaves as 1 over z. Then I just pick the residue and I get f of 0. So let's even say it's holomorphic in the disk. It's also true if it's holomorphic in the disk. But then if the function is holomorphic in the disk, I can write this as, I can basically change this contour from a contour around epsilon. I can go to a contour around 1. I can go to a contour on the boundary of the unit disk, right? So I have a contour, I blow the contour, right? So instead of integrating around epsilon, I integrate around the boundary of my unit disk, right? Or right close to the boundary where I am. And because I'm at the boundary, and because f is bounded, this is smaller or equal than the integral on the boundary of the unit disk. We can write like this, d theta over 2 pi, k of, at the boundary of the disk, e to the I phi, times 1, because remember that f is bounded. So f is smaller or equal than 1 at the boundary of the unit disk, right? That was the condition. And so any k that you choose, you put here and you get a bound from the other side. Now, like before, you try examples, but now you write examples for k, right? You try an example, any k you want. It can be k equal 1 over z plus 1/2. That works. You plug in this expression and you get some value, right? And then you take 1 over z plus z squared. No constraint on k, right? Any function that has a pole at 0 works, provided the pole is with residue 1. So you put many k's, you try many k's, many examples. And what you are doing right now is always putting a bound in this direction. So what you are doing is...
Sorry, on the right-hand side of your inequality, did you want mod of k or k itself?
No, excellent. Sorry. Good. Modulus of k. Great. So any k you put, you take there, you put the modulus of k, right? So, and this is at the bound. And so now you take this k equal 1/2 plus 1 over z, you get some value. You take some k, another k, say k equal 1 over z plus z squared over 100, and you get another value, and you get value. And here, you are very smart, you try k equal 1 over z. But you see, k equal 1 over z, the absolute value is 1, this just gives 1. Right? And so we sandwiched the bound between 1 and 1, and therefore we proved that this g is equal to 1. Okay? So we answered by just sandwiching it. So before, we had constructed solutions that were better and better, and eventually they approach 1, the function f equal 1. But then we also constructed dual objects, and eventually we were smart and we constructed this. This problem, in this kind of problem that we are solved, is called the gap, or the duality gap in this case, because it's the gap between the primal problem and the dual problem. And what we would say is that the gap closes, which often does for many problems of optimization. So here, the gap closes. And we proved this theorem, this Schwarz lemma, if you want, and we established that g is equal to 1, because on the one hand, it is for sure smaller or equal than 1. On the other hand, we constructed an example which gives 1, and therefore the optimal bound is 1.
So, sorry, Pedro, can I ask a question? We used, of course, the holomorphicity, etc., of f of z, but where did we use that it's real analytic?
No, real analytic is just so that I don't need to put absolute values of f of zeros, right? I want to say what's the maximum of f of 0 at the origin. Otherwise, I have to put absolute values everywhere. It is just so that I assume it's real at the origin. Otherwise, everything would go through. I just need to put absolute values in at the origin.
So for anything which is real at the origin, I guess. Huh?
It doesn't need to be real. If it's not real, multiply by the phase that makes it real and maximize what remains.
Okay, thank you.
Yeah, and so.
Pedro, can I ask another question?
Of course.
So
Yeah.
in the primal problem, it's never guaranteed that you'll find a suitable n such that the gap closes, right?
That's right. So in a primal problem, all you do is you see that the points are converging or not. So you pray, right? I mean, if it looks like they are not moving, you probably converge, but it's true.
But rather than praying, is there some systematic way of developing the primal problem? I'm just wondering if it is.
No. I think praying is the best.
Okay.
And I will even tell you why, because sometimes right now it looks academic, right? I put 100 and I put 200 and I see it's the same. Of course it converges, right? But when we will be doing with amplitudes, for example, I'll show some examples where you start with an ansatz, and as the n increases, your amplitudes can start doing new things. And amplitudes might want to develop resonances, new bound states, new particles. And that really can require, there are critical values. At some point, a new resonance comes in, and now the bound jumps to a new plateau. And then at some other point, and this does happen. So
right. Yeah, thank you.
So this is because you cannot ensure that you are sweeping the entire allowed space, right?
Yeah, because, okay, here, functions of one variable, if the function is holomorphic, if I put up to power 100, okay, I can describe anything. But that's because it's very simple. It's a function of one variable. So let's emphasize that these are two different problems. So this problem here is a problem that is linear, right? Because the target is just F0, right? It's linear. It's a linear problem, but it's constrained, right? There are constraints, right? The other one, as Shiraz pointed out, that I had forgotten, what you do is you just, how do you do it in a computer? You just minimize, you just ask to minimize what? The integral of k of z, right? Of the absolute value of k of z, as Shiraz pointed out, where you put k to be what? Anything you want, 1 over z plus any expansion of kn z to the n. And now it's unconstrained, anything, right? You put a pole plus anything holomorphic, right? So now this problem, this dual problem, it's unconstrained. That's great, but it's nonlinear because of this absolute value that Shiraz pointed out. And so what's great is to have both. I mean, you have on the one hand the dual problem that excludes and that says, for sure this is excluded, no way. And you have the primal problem that says, for sure this is allowed, right? And so what we reach typically is this picture where we have an allowed region. This is allowed, and we know it's allowed for sure because we can construct primal solutions. We can have a dual that is excluded. This is excluded for sure. And it's excluded. And the better functionals you have, the more you exclude. The better imagination you have to construct primal solutions, the more you include, right? And then in the middle, there is a gap that sometimes closes, but it doesn't a priori need to close, especially. You might need more conditions to close, or you are not guaranteed that it closes. Okay.
Pedro?
So,
one question.
Yeah.
So in this case, you said that, the solution to the primal problem, below that, everything for sure is allowed, right? That because you kind of explored all the conditions, but in problems such as scattering amplitudes and such, you will never be sure that something for sure is allowed, right? Because there could be some other conditions coming from, you don't know. And those may not may not allow such a solution there in the naively allowed region. So what you could be certain of is that the excluded part is excluded even by analyzing a single condition.
I agree.
And then if that is so, then is there a meaning to the gap and the closing of the gap?
Mathematically, yes, right? Because I say based on this particular problem where I will be studying So indeed, just so that everyone may understand, so what we are discussing now is that we'll generalize this picture to the S matrices, where we will have here, we will claim that we have a region of excluded S matrices. There are no theories that will have these excluded S matrices here. And then we will have some region that will say it's allowed, but allowed, as Abhijit is pointing out, is a dangerous word because it's allowed, for example, by all the constraints that we get by studying 2-to-2 scattering, for example. And of course, this region can decrease if I impose more conditions like 2-to-4 scattering and so on. So the allowed region depends, right? Today something is allowed, tomorrow I impose more conditions, it gets smaller. Whereas what's excluded is excluded. And eventually I can find more principles and exclude more. So that's true, and we will see that. So this we call the desert, no one is here, it's forbidden. This is allowed, we call it the garden. And of course, in the middle, there is the swamp. Okay. So that's the picture that we would like to try to develop a little bit.
Pedro, in the case of the conformal bootstrap, the allowed regions would happen by considering known examples of conformal field theories.
Great point. So the CFT bootstrap is this type of bootstrap. So for those that follow CFT, so this revival of the CFT bootstrap is in this style. You exclude. You find functionals that say there is no CFT for sure with these dimensions or these 3-point functions or this and that, right? But then you have primal solution, which is, you know, that there are the minimal models and so on, which are points that you can put there, and no one can exclude those. And you could also try to develop some CFT bootstrap where you just construct many solutions, and then you'll be drawing some garden. But the CFT bootstrap is a good example of this type of bounding.
So there you are sure that the bound that you got from the dual method is optimal by realizing that there is actually a theory that saturates it. There is something that is physically allowed that saturates it, right?
Yeah.
So here, to be sure that a bound is optimal, one would have to do a similar thing.
And I suppose you can in some cases, right? Like you can look at scattering of sine-Gordon model or something like that.
Yeah.
Right. Yes. So in some examples, so since people know all this, so in some examples, we know, for example, that an example that I'm not going to discuss today, but that is, for example, in 2 dimensions, there is no swamp, the garden closes, the garden and the desert touches, and sine-Gordon, for example, is at the boundary of the garden. And so it is allowed for sure, and therefore there we know, for example. And of course, to say what the x's mean, I would have to say, what am I plotting? What do I mean exactly? But if you want, I can tell you, but it is just an example where there we know that we converged because for sure this theory exists.
It does closing of the, so this is a slightly different question. Does closing of the swamp, would it give some physical insight into the kind of assumptions that one made for the primal problem? Meaning that, you know, all the conditions that you put are actually sufficient to, you know, to say that things are allowed or not. I mean, can one say something about completeness of our low energy constraint?
Yeah. So I mean, in general, it's not complete, right? I mean, the short answer is that it's never complete. 2-to-2 is never enough. You need 2-to-2, 2-to-4, and so on. And we know, even in 2D, we also know something we studied with Andrea, for example, and Alexandru, were simple examples in 2D, where you can consider, for example, 2-to-4, even into this too hard, but you can consider different species of particles, like a light particle and a heavier particle. And you see that you get some primal, but you impose conditions of the heavier particles and the primal goes down. And that's what typically you expect. So quantum field theory would be defined in this language by the set of all amplitudes, not by one amplitude. And so if you impose one amplitude, you get something. More amplitudes, it goes down, 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 down until you reach the correct boundary. Now, if you are lucky, one amplitude already will give you a very good approximation to the correct boundary. That's the best you can imagine.
So in
the same way that in CFT bootstrap, one correlator or 2 correlators often give you a spectacular boundary to the CFT, right?
Right. So just one more question now that the sine-Gordon model has come up. I mean, there are other types of models, also integrable models, things that have a rational versus trigonometric and elliptic and so on and so forth, right? So why is it that this trigonometric S matrix appears, and what happened to the rational one? I mean, does it live on the boundary of the space or not?
No,
something like Young's matrix.
There is a beautiful story into these elliptic S matrices appear, for example. There are beautiful.
The rational ones also live on the boundary?
They also are at the boundary. I can show you some spectacular plots. But if I go in this direction, I will not tell you about gravity. So
okay.
I think that the others will not be happy.
Yeah, we'll talk to you offline about that.
Yeah, we can discuss afterwards if you want. I can give you an extra half-an-hour seminar at the very end about this elliptic stuff and all this 2D. I'm happy to do it. Yeah. Okay, so let's So let's summarize a little bit just what we did here, because now we are going to generalize it. So first, we had a target, something we wanted to explore the space that we were going to use as our measure of our label of what it means to be in the space or not. And in this case, we chose the value of the function at the origin. Then we had a dual formulation where we just constructed some dual object, K of Z, and we put rigorous bounds. And finally, we had a primal formulation where we construct f of z's and we have inclusion plots. Namely, we say this is allowed, and we hope that the inclusion plots converge towards the bounds. And so now we would like to repeat these kind of things and to think, what would we do in the case of amplitudes? So the first question is, what would be the target? Okay. So let's pick a good target, a good function to start. So, let's study the space of 10-dimensional theories with a maximal supergravity, with maximal supersymmetry. And such that their scattering amplitude, they have an amplitude, that is a function of S and T. Okay, let me write S, T, and U. This is a bit misleading because S plus T plus U equal to 0. These are just the usual Mandelstam variables. Such that my scattering amplitude, because of supersymmetry, is given by some supersymmetric delta function, some delta of Q, times some amplitude A, meaning that all components are related. So if I have a theory with maximal supersymmetry, if I know to scatter 2, 2, 2, all other particles are related. So let's just remind ourselves, for example, at tree level, we would have that this A would be 1 over STU at tree level. Right? And therefore, and then by studying, and this doesn't look like a regular scattering amplitude, right? This is the usual thing that people say, 1 over STU doesn't look like a scattering amplitude of a field theory. It's a funny thing, 1 over STU. But from this object, for example, you can ask, what is the scattering of 2, 2, 2, for example, for an axidilaton? Which means that you extract some power from this delta function, S to the 4 over STU, which now looks like something like S squared over T plus S squared over U. And now it looks like a regular scattering amplitude at tree level, where you just have some exchange in the T channel plus some exchange in the U channel, right? Here, the axidilaton is charged, so there's no annihilation, no exchange in the S channel. There's only T channel and U channel. And they are just exchanging a graviton, which you see by this power 2 here. Okay. So this would be an example at tree level. So you take this 1 over STU, and now you take different components of the delta function to extract gravitons, axidilatons, and so on, all the supermultiplets, right?
So,
now,
sorry, Pedro. Q
Yes.
is then some function of STU, is it? The argument
Q is where the polarizations are. It's like a generating function. You see, when you have supersymmetry, right, it means that the scattering amplitude of axi-dilaton to axi-dilaton and graviton to graviton are proportional to each other. If you know one, you know the other, just the proportionality. And that proportionality is in delta of Q. So delta of Q is just so that you don't need to study all these polarizations. And the beautiful thing, you need to study a function only. Okay. Now, more precisely.
Sorry, and actual amplitudes always have at least a fourth power of momentum on top of the STU. When you extract actual amplitudes of actual particles.
Yes. Yes.
Okay, thank you.
That's just dimensions. Yeah, that's right. And this one here, let's just be careful that this one is basically L Planck to the 6, I believe. And so this is just setting our units. So by saying the amplitude starts at tree level with 1 over STU, we are measuring things in units of L Planck. And then we have corrections to this. This would be at tree level. And then we have a low energy expansion. What would be the low energy expansion? It would start with a constant, alpha. And then there would be the next term that if you know tree level, you know that is the one loop correction, it's just gluing together to tree level. So there will be some one loop logs that have some power of S. They are of order, these guys compared to these are of order S, if I believe correctly. And Andrea, who is here, can correct me. Plus ...
So the first correction is a constant because the first correction to supergravity is at R to the 4.
Yes.
Riemann to the 4. And that follows from supersymmetry, I suppose.
That follows from supersymmetry.
Thank you.
And you see, you could imagine, why can't I write something with less powers? Compared to STU, it's 3 powers, right? So you could factor out 1 over STU and try to write something with less powers, right? And so first, as you say, by supersymmetry, it's not there. If you try to write it, you also see that it would then, if you describe it like this, it would correspond to some higher spin particles of massless. So you would also not want them anyway, right? Because it would give some higher powers of S in this case.
Okay, but supersymmetry is essential, right? We could have had a Riemann cube term, for instance, in a non-supersymmetric thing. Yeah. Okay, thank you.
Good. So now that we normalized L Planck to 1 for the first term, alpha is a great target, right? So this is our target. So our target is what we would say the first Wilson coefficient to the supergravity, correcting supergravity. So the target will be alpha that shows up in our scattering amplitude. Our scattering amplitude is delta of Q over STU. If I factor out 1 STU, it would be 1 plus alpha STU plus terms much smaller than SQ. So in the same way that our target here was the value of the function here at the origin, here the target will be given by the first correction to the amplitude. Okay. And now different UV completions of gravity will have different alphas.
Sorry to interrupt. So the fact that there is this, that the index structure is just completely determined, at every derivative order, basically that's telling you that the only Riemann to the 4 with the various derivatives at any derivative order, that all of these, there's a unique such structure consistent with supersymmetry up to field redefinitions at every derivative order. Is this right?
I think so, yeah, I think that's correct. Yeah.
Okay, thank you.
At every derivative order, Shiraz, or just at R to the 4?
No, I think at every derivative order, because it's coming just from the fact that this all index structures is in this delta function, and then it's just a function of S at T.
Yeah. So it's really a function. It's really one function that we have to bootstrap.
So yeah, that's what, if I can ask, so that the maximal supersymmetry is probably going into that statement, right? Mm-hmm.
Yes.
Thank you.
So this alpha I should think of as, sorry.
It's like in n equals 4, if you have a MHV amplitude, you just write some delta function, then everyone is proportional to everyone. It's exactly the same thing. Okay, maybe for some people. I'm not sure if it helps everyone, but it's the same thing. So that's why, even though
Pedro, so alpha I should think of just as a classical piece, or is it because of quantum effects? Or?
No, it's really quantum. Here it's really, this is definition of alpha, right? It's the first correction to gravity in the scattering amplitude of 2 to 2 gravitons.
We are not considering string theory here.
No.
Okay.
That's the goal of the title of the talk, right? So,
yeah. Sorry, and just to follow up on Abhijit's question, in general, amplitudes will be non-local. So won't admit an STU Taylor expansion when you have massless loops. Isn't that right? So what sense does this Taylor expansion make if we're
so there are terms here, these terms, but they start at higher powers of S. There are terms here like S, log S, plus dot, dot, dot. These are there.
And this you can prove again from supersymmetry? How do you know that the non-locality starts higher order?
So here I'm assuming that the rules of the game are the usual rules of quantum field theory. I start with supergravity, and I start correcting with irrelevant operators and doing loops and adding more and more counter terms. If it's something more fancy than that would be beyond the usual paradigm, you are right. Then this would not work.
No, but since we've got massless particles, it's not clear that there is a derivative expansion of this theory. Right?
No, that still exists. So the loops do come with higher powers of energy. For example, you get 3 level, right? It comes with some, you compute some phase shifts and you get some 3 level. Then at one loop, the phase shift is a 3 level square. And the 3 level phase shift comes at a power S cube or something like that. So the one loop would come at S to the 6. So things are organized by powers of energy.
Powers of energy, but there could have been at one loop, say, a log of energy of S.
There is. That's what I wrote here. S log S. There are logs.
Can I just say one thing, although I know the subject very poorly? Shiraz,
there are logs. There are logs. I'm not saying it's a regular expansion. I'm not saying it's holomorphic at all. It's not. There are logs.
I see. But then, I see. You're saying that this is just a dimensional expansion.
Yeah.
Where the dimensional expansion could include logs. At each order, these functions could include. Now I understand.
A minus 1 over S TU, right?
Yes.
And then a limit when S goes to 0 of this object exists.
Oh, sorry. Yeah. I thought you were doing a Taylor expansion or a Pauzi.
No.
Okay, thank you. Yes.
It's an expansion, but in dimensions. And there are logs for sure. Yeah.
So what sort of diagram gives you alpha? What sort of diagrams will give you constant contribution at loop?
This alpha would be from R to the 4, as Shiraz said.
No, but if you want to start with some Lagrangian and compute loops, and you want to think of alpha not as coming from tree level terms, then what is the other source of alpha? The way logs are coming from loops.
Yes. No, but I think loops would always give you higher powers of energy, I think.
Right. So this alpha really is the tree level piece then.
Yes.
And then you are extremizing that.
Yes.
For a consistent.
Yeah. Again, supersymmetry is essential for the statement, right? Because just in Einstein gravity, just at R squared, you would get some logs.
Yeah. Oh, yes.
Okay.
Obviously. Yeah.
Yes. Okay. Thank you.
And sorry, I didn't quite understand. So just Einstein gravity. If you want to make it, if you want to supersymmetrize it, you automatically end up with R to the 4 terms. Is that, maybe I missed what you said?
No, I was saying that in Einstein gravity, you would get corrections below R to the. Suppose you just started with Einstein gravity, then you did a 1 loop correction to that. The quantum effective action would include something at below the alpha.
Yeah.
Okay. Right, and that would generally have logs, right? Because you'd have IR depth, the IR.
So 10D maximal supersymmetry is crucial. I mean, it's really cool.
I guess one way
otherwise
to
it's much more complicated. You have to deal with indices that some of us, like Shiraz, is not afraid, but I am. So I have one function.
So Pedro, just so because you are allowing a tree level term, then why can't you allow other tree level terms also? Is it because they cannot be supersymmetrized?
lower
R
order,
cube term,
yes.
let's say.
Lower order,
at
yes.
tree level.
But at this order, it's the only thing I could write with this order. With this energy power.
No, how about an R cube term? Because
it's
that's not
inconsistent with
supersymmetry.
maximal supersymmetry.
It's
Yeah, that's not there with maximal supersymmetry. Yeah. Then you can have higher powers. You see, if you factor out 1 over STU, did I factor out somewhere? If you factor out 1 over STU, this term is proportional to STU, right? And it's the only thing you can write, which is crossing symmetric, which has dimension 3, right? So it's just STU. SQ plus TQ plus U cube is the same. So you just have 1. Then at S to the 4, you could have more. At S to the 5, you could have more. But this is the first one. And a nice thing is that even though we are dealing with massless particles, even though we have logs, the logs show up 1 power of S later. So we can subtract them when we can take limits. This defines alpha. This limit is well defined. If it was not, if the logs show up at the same order, it will not be a big deal because the logs come with very precise coefficients that are determined by tree level. So we would also be able to subtract them out easily.
Okay, thank you. Sandeep, you were saying you had a comment which I interrupted. Sorry.
No, never mind, Shiraz. That wasn't very important. All I was saying was that the logs for massless particles you can compute in effective field theory anyway, so you would know their structure. Oh, okay, and never mind. But just to ask Pedro, so I understand the flow of the talk, are you saying that, say, if you take string theory, we would be able to compute alpha, the R to the 4 corrections?
Yes.
But what you want to do is just ask from the S matrix bootstrap what constraints you can put on alpha, right? And compare it with whether, say, you would get the value only allowed in string theory or you get something more general, roughly.
That's absolutely right. That's what we wanted.
Okay, thank you.
Sorry, Pedro, just to understand.
It's good. Lots of questions.
So if I were to add, terms that are larger than alpha at small s, 1 over s or something like that, why? What is the problem? You said something, but I mean, this is certainly allowed by supersymmetry because this multiplies the delta Q. Is it because it's some non-local or something? And I don't understand. So what I mean is, before alpha, why can't there be some 1 over s?
Are you thinking of adding something like 1 over STU square? The square of the first term, right? It would have lower dimension, but that's not local, right? That's not something that you will...
No, not 1 over STU squared, but let's say 1 over s, just 1 over s or something like that, appropriately crossing symmetrized.
Yeah, a square plus t square plus u square by STU.
1 over s properly symmetrized will 1 over s plus 1 over t plus 1 over u is equivalent to would give an I think that is, sorry, one second, it's st that I forgot. I think it's r squared. Yeah, I know it's not there by supersymmetry. It starts with alpha, but that one that you are saying, let's see. Yeah, that will be exactly, if I factor out the 1 over STU. Oops. If I factor out 1 over STU, right? Then I'm saying that there is 1, and then there is alpha times STU. And you are again asking, why can't I have some beta times s squared plus t squared plus u squared, right? And the answer is what Shiraz already said. It's because by supersymmetry, this term would correspond to an r squared that is not there.
No, but this multiplying delta of q, so it's manifestly supersymmetric.
Okay. But yeah, delta of q is one consequence of supersymmetry, that all of them are related to delta of q. It's not the only one. I mean, the fact that the fact this beta here that is 0 in string theory, we are assuming this beta to be 0. If you want, we would be studying a section of theories. I think beta equals 0 is also a consequence of just imposing supersymmetry. This is the usual thing, that if this beta would correspond to r squared, that cannot be supersymmetrized. I don't know how to prove. If you ask me, can you prove that beta is 0? I mean, I'm not yet. I mean, I'm starting to learn all these papers. I don't know. Okay. Maybe Shiraz can say a few words. In 10D, in string theory, it's 0. That I know. And we could say that let's assume it's 0. It's the only thing you could write. You're right. You could write this term. Let's assume it's 0 and explore the space of theories where this bit is 0. In 10D string theory, it is 0.
Yeah, certainly.
There is no obvious. Yeah, sorry.
I was saying something a little not very interesting, but I was saying that if you assume a local expansion of the action, you can show that it starts at 4. More than that, I'm not sure.
Yes. So, for example, if this term was there,
locality and supersymmetry.
Locality and supersymmetry, like Sethi and company, Sethi and Paba and company.
Because you see, for example, this term, if you expand, will give you terms like you have here some s to the 4 over t, right? This term, if you expand this term, right?
Sorry,
this
I'm not seeing. Are you? Yeah.
Here.
Yeah.
This component, right? Now you are asking multiply it extra by some extra power here, right? Now you will contain them like s to the 4 over t. So that's like a massless spin 4 particle, right? And we said we have just supergravity. We don't have this massless spin 4.
So it is not s to the 4. It will be 1 over s. 1 over s plus 1
no,
over
because you extract a component s to the 4 from here, plus an extra s
okay, I
there,
see.
plus
Yeah,
extra u. So
okay. Yes.
You will have a hard time interpreting.
Yes. Okay.
This doesn't happen with this one, right? Because this one, the STU cancels the STU, and you just like contact interactions that you extract.
Yeah, contact
don't have any issues interpreting that.
I see. So you're saying this corresponds to exchange of some higher spin kind of thing, and that you don't want, and so on.
Yes, exactly. So this one you can explain with supergravity. This one, it's okay, it's just contact. This one, it would look like spin 4 and stuff like this. And furthermore, I think based on supersymmetry and the local action, you can exclude it.
So it could also be a goal to show that beta must be 0, right? Without assuming locality or something. Just
that's an excellent point. Yeah.
Thank you.
We could more generally just say, okay, let's forget. Let's put beta and see what happens, and let's explore the space of beta. That's an excellent suggestion. Yeah. Let me put here a remark, not to forget. That's a great point. Okay. So what are the rules of the game then? What do we do? So now the second step that we had here in this primal formulation was we had to know the space of functions. So we had to write that f of z was our target, f of 0, plus some holomorphic sum. Some sum of fn z to the n, and I took out f of 0. So now this sum starts at 1, right? So now we need the analog here. So now we need the analog of this statement that says that my amplitude here will be the amplitude A, which doesn't have this double line here on the top, is just what multiplies the delta function. We have to say it's 1 over STU plus alpha, and then alpha is our target, right? Like here, f of 0 was our target. Right? Like here, f of 0. Now here it's alpha. But now we have to write the analog of this UV completion of the holomorphic functions, right? So now we have to write the rest, which is not a Taylor expansion, as Shiraz pointed out. It's not like it's obviously not a Taylor expansion. So now we have to write plus the analog of these wiggly lines here that parameterize a general amplitude that is that would be crossing symmetric that could appear. So this would be like parameterizing this UV completion. Okay. So that's step number 2. Then there will be a next step, which is this find max. As Mathematica, find the maximum of f of 0 subject to some constraints. And then there will be an analog on the amplitudes. Okay, so what do we know about this amplitude A? So this amplitude A is an amplitude for massless particles. So it's a function of S and T, but let's think that it's a function of S, T, and U. And this function has cuts, as Shiraz is pointing out. So when it has cuts that, for example, if you think in terms of S, you have a cut for S bigger than 0, which are related to all the multi-particle processes that you can have. So the leading term, the leading behavior at this log, you can predict just by gluing 2-3 level stuff. And then as you go to higher and higher loops, it's very complicated, but there is a cut there. Now, the idea now is that this function, however, if you fix t, then this function has another cut here, the u cut. This would be the u cut if you say fix t, right? So then in the S-plane, there is also the u cut, and the u cut moves, right? It's a function. It's at the u cut starts at minus t, right? Something like that, when u is positive. Now, but now what we can do is the following. We can think like this. Let's think of our amplitude, not as a function of s as fixed t, but let's think of it as a function of really s, t, and u as if they were independent. Namely, what we are going to think is that this function takes value in the following thing. It has unit disk without the cut for s times the unit disk without its own cut for t times the unit disk without its cut for u. So we imagine a function that takes value in these cut planes. So there is a cut plane for u, a cut plane for s, and a cut plane for t. And then we think that this a is a general function. We think of it as a function that takes value in the product of 3 unit disks. But then we impose the constraint that we are not in the product of 3 unit disks, but we are on the constraint surface that s plus t plus u equal to 0. So we generalize to a bigger manifold, which is 3 disks. Sorry, I said disks, it was already too fast. 3 cut planes with the constraint that s plus t plus u equals 0. So it's not an analytic continuation, it's what is called an analytic extension. When you have a function that's a function of 2 variables, and now you say I want it to be a function of 3 variables instead, and then I restrict to 2 variables by a constraint. Now, you could ask if this is a dangerous step. Can I always do it? Can I always start with 3 variables? Can I start with 2 variables and now say, oh, it's a function of 3 variables plus a constraint that puts me in a section where it is? And the answer is no. In general, you cannot do it. In general, if you enlarge to a bigger space, you will find singularities in this bigger space, and you cannot extend it without introducing more singularities. So when can you do it? When can you extend from a space to a bigger space without these obstructions? And there are theorems in mathematics, and there is a theorem that says that if your manifold is something that is called Stein manifold, and if you have a submanifold inside that is also a Stein manifold, you can go from the small to the big without singularity. And this cut plane is a Stein manifold. Product of Stein planes is a Stein manifold. And s plus t plus u is an holomorphic constraint, and all these holomorphic constraints define sub-Stein manifolds. And so this is an example. You have these 3 unit disks plus this constraint that defines a manifold that is inside just the 3 disks. I'm always calling it disks. It's better if I explain why I'm using this, but okay, it's the 3 cut planes, and therefore I can always do it. I can always think of it as a function of 3 variables with this constraint. Okay?
And with no singularities apart from the cuts in the full 3-dimensional.
Exactly. That's the advantage. So the disadvantage is that we have 3 variables instead of 2. But the advantage is that the cut is not moving. Right? This cut moving is a pain. If you have a function where the cuts are moving, it's annoying. Okay. Then this means something powerful, because it means the following. If you know that you have this function, then you can think from a function of s, I will Taylor expand it around some point here. This point could be s equal minus del Planck square, right? S equal minus 1 in units where L Planck is equal to 1. And now I can Taylor expand it here. Well, Taylor expand would be stupid because I would eventually reach the cut and then it would stop converging, right? But it's easy. I can just foliate the plane with some variables that map the complex plane to a unit disk that surround the cut like this. And so I can map this cut plane to just a unit disk. So I have the unit disk where this part of the cut here would be this part up here, and where this part of the cut would be this part here, and where the circles that I drew here would be just concentric circles here. And so now I have this variable that maps the cut plane to the unit disk. Let's call it rho. This is rho of s. And then in the rho plane, I just have the unit disk. And I have functions that are holomorphic inside the unit disk. And so now we can write we can write an ansatz for our amplitude. We can say that our amplitude Okay, let me write it actually here. We can write what this dot 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 would be, this thing. Now we can say that we can write that this would be a triple expansion, a sum, with some coefficients C that are symmetric, N, M, K, they are fully symmetric, times rho of S to the N, times rho of T to the M, times rho of U to the K. Where these rows, again, map the cut plane centered around, say, minus L Planck square to the unit disk. And these sums, they go a priori up to infinity. In practice, we truncate it at some big number N. And this big number N is the same type of big number that we truncate in this example of the holomorphic functions. Now, exactly like this, it will, okay, let me put some prime to indicate that by this prime, it means that I tune these coefficients just a little bit so that the leading term doesn't have a constant because the constant is already outside. Okay, so this prime is just so that all the low energy is explicitly taken out. So there is a low energy part. And then I tune this such that this contains all the high energy part. In the same way that here I took out my target and then I have the rest. Okay, so this is the analog of this step of writing an ansatz. Is you write down such an ansatz. Note that these rows are nice variables because to do this kind of things, because you see low energy is this. This is the point where you have low energy. This is where low energy is. This is where high energy is. So if you write something trivial, like rho of S minus 1 square, for example, right? Then this vanishes when rho equal to 1. So this is something, it turns out to be S for S very small. But it's finite by definition, right? For S very large. Because it is just inside the unit disk. When rho is 1, it's just finite. It's 2, it's 4, right? I don't remember that. So it's a nice basis that you write things that it has whatever expansion you have at low energy, and then they are finite by definition at high energy. Okay? So it's like, of course, it's not unitarization, but it's good variables to describe things if you don't want things to blow up all around.
Pedro, one question. So the fact that you are expanding not quite at low energy, but some medium energy, and then trying to say that at low energies it should behave in a certain way, would that not, I mean, be kind of not very good for numerics in the sense that depend on what you choose as big N and so on? If the low energy were somewhere in the interior, which would be the case if you have mass gap, that would have been kind of nice. But would this be a problem a priori?
Yes. I mean, problem, no, but it's something interesting. So here, as Abhijit is saying, I'm choosing where to center this expansion. So for example, we chose in our numerics, to be something like minus 0.7 L Planck square. Okay, or just a random choice a priori, right? So if you put any value you want, you can. Doesn't matter, right? It will eventually converge. But it could be, and it does happen, that different values converge much slower, right? And why would that be? Because it could be that your theory that saturates the boundary wants to put resonances at some multiple of M Planck, right? And so it wants to probe that some scales, maybe small light resonances, maybe heavy resonances. And therefore, this point, if you put a not clever point, the numerics will really struggle to give you to converge. So we do some games. So we found out experimentally that this is a good point to expand around. But in massive case, you are right that there is a mass, so there is a natural unit to expand around. Here,
so
the mass is by L Planck.
I didn't quite understand this point about the resonances dictating a good point of expansion and other things dictating a good point of expansion. Could you say a little bit more?
Yeah. Suppose
why there should be a good point?
Yeah. Suppose your theory has a resonance at S equal 3 plus I. Now, what does 3 plus I mean? It means 3 plus I in units of L Planck square, right? So it's at 3 plus I in units of L Planck square. And now imagine this point is here. Oh, oops. Imagine this point turns out to be mapped here. And the other reference that you want to study is mapped here. And the other one you want to study is mapped here. This will be a bad choice of variables. By choosing a different origin, maybe we'll have one resonance here, another one here, another one here, and now they are more spread out. So a Taylor expansion will much more easily capture them, right? So two different scales. One scale will put the resonances all grouped together. Another one will give some nice spacing between the resonances.
Right, so the optimal choice for the expansion point is on top of the resonance zero, or close to it. What is the statement?
No, there is no precise.
I mean, in other words, could you have made this 0.7 even better and better? Is it like is it finding an optimal point, or is it just I don't, yeah.
But unless it's a very important point, let me discuss that point a little bit later. It's not
okay. Thank you.
There are so many other points in the numerics that are more crucial than that one. That one, if you have some mass scale, put the point at any multiple of the mass scale. Here we put 0.7, we could put 1.3, it would be the same.
I was thinking maybe the fact that this massless theory is a crucial, and this is where it's showing up. That's why I was trying to probe it. But yeah.
No. This is not crucial. I mean, you see, you have a scale, right, which is given by L Planck that you set to 1. So that's where you measure your things. So it's massless, but you have that scale, right? So you have L Planck. Okay. So you measure things in units of L Planck. So you put it at L Planck at minus L Planck square times 0.7, but it can be times 1, but it doesn't matter.
Okay.
Okay, good. So now we have an expansion of the amplitude. So now we can already take this amplitude, and now we can ask Mathematica for find max of alpha, a linear target like this one, right? But now we need the constraints, right? We need the analog of these constraints that I remind you was that the absolute value of f at a bunch of grid points Zi were smaller or equal than 1. And now we need the analog of those constraints here. Right? What do we do here? And this is unitarity. So that's where unitarity will come about. Okay? So we already used crossing, now we use unitarity here. So what is unitarity? Unitarity is the statement that, now unitarity is the following statement. Let me write it, and then if there are, I can explain if there are questions. That if I write my amplitude A, A was what multiplies delta of Q, remember? So let's extract this oxydilaton like I did before. So A times S to the 4. This is the scattering of the oxydilaton. Now I take this amplitude and I write it as a sum of Legendre polynomials. Well, in this case, it's some kind of Gegenbauer polynomials of L. It's 10 dimensions, so it's some 3/2 power. And I decompose them with respect to cosine of the angle. This L is the spin. And then here they will be multiplied by 1 minus an SL of S times some Jacobian, some phase factor, JL. So here I'm just decomposing into spins. There will be a sum over all even spins. Now this guy here is basically what is the S matrix for scattering two particles in a two-body state of definite spin and staying in the same spin. So the probability that you scatter two particles, you prepare a two-particle state, and you prepare it at some incoming spin L. So in the out state, you have some state of the same spin L, right? But it can be two particles or it can be multi-particles. So if you ask, what's the probability that if I start with L and two particles, I go to two particles, that is the absolute value of this function SL of S. And therefore, the constraint is that this S value needs to be smaller or equal than 1. So that's unitarity. Okay. And so what do we do now? Okay, now we go back to these unit disks, and what we do is we put a grid, because we put a grid here in the unit disk like before. And then we have many points Si, or in this case, rho I at the boundary of the unit disk. And therefore, this condition here, now the analog of this condition is now that the absolute value of the SL at all these points Si is smaller or equal than 1.
Pedro, can I ask a question? So
yes,
there is a weaker unitarity condition, which is the imaginary part of these partial wave expansion coefficient being less than 1. So that would have been a linear condition rather than a nonlinear condition.
Yes.
Would that give you anything? Would that give you anything?
Yes, it would. It would. Let me. I want to emphasize that. I hope I don't forget. So let me mention that when I will show you the plot in the next slide.
Okay, thank you.
Great point. Yeah. So what Ananda is saying is that there is a much simpler condition from unitarity, which is that the imaginary part of the amplitude at t equals 0 is positive, right? The usual optical theorem. So that follows from what I said, but it's a weaker condition. So that is we could just ask, what would this give if I just impose that this imaginary part is positive? Okay.
And sorry, this is weaker to start with because it's one condition, whereas you had an infinite number of conditions, one for each L. Is this right?
That's one of the that's true. Yeah.
Thank you.
So basically, what's happening is that we are saying that this object here, right? This is the phase shift. It lives. Each of them lives inside this circle, right? Right. So this is the statement that this S is smaller than 1 is the statement that this quantity is inside this circle. In particular, a weaker condition is the statement that it's in the upper half plane, because the circle is in the upper half plane. So this is just imaginary part positive for one spin. And then if you sum over all spins, the imaginary part is positive, because it's the sum of positive things. So it's weaker in two senses. It's weaker because it goes from a circle to just saying it's up. And it's weaker because it goes from being one spin to being a sum of all the spins. So it's much weaker.
So Pedro, how does one deal with T-channel poles in this approach? Because in the previous slide you said T going to 0, right?
Yeah. So the poles are factored out. So whenever I write an expansion, you see I took out the poles. The poles I know once, and that's it. And then there is an expansion after the poles.
I see. So there is some assumption about there is only one particle and so on.
That's right. So the behavior at equals 0 is just the pole.
I see. Okay.
Now you see that now we have now we could a priori put in a computer. Now we ask maximize alpha, where you put these constraints here that this is true. Now let me emphasize how this is done in practice. Let me emphasize that it's easy on the one hand, but it's hard. So to extract this SL, you see, you have to extract this SL, right? So how do you extract this SL? You just...
Sorry, Pedro. Sorry to bother you, but this amplitude should be the full amplitude. Only on the full amplitude can you impose the unitarity, right? In other words, not after taking out poles.
That's right.
So this amplitude, this condition needs to be put on the stuff, including the pole.
That's right. So this is the full amplitude. You take the full amplitude, you decompose it like this.
Yeah.
In particular, if you just
then my question applies at t equal to 0. How to deal with t equal to 0?
Yeah. So this t enters here, right? So this is t plus s. This is what? T plus s over. Okay, I forgot exactly. This angle is a function of s and t, right? So it's this
1 plus 2
1 minus 2t over s, right? It's like this.
Yeah.
So the summation over all spins produces a pole. So if you put some Pocammers for this SL, you reproduce the 1 over STU, for example.
Okay.
So that's easy to reproduce. So that you can find in many papers, like Simon Caron-Wood, for example, as the expression.
1 plus 2t over s.
Sorry?
No, stupid point. 1 plus 2t over s.
Yeah, I always forget this idea. Okay. So so notice that this SL, basically I can write the following equation. SL is given by a linear operation, a linear operator that depends on L acting on the amplitude, right? Because it's just integrating, right? You multiply by some, use some orthogonality of Legendre polynomial, so you just multiply by some Legendre and integrate, which is, so it's like a linear operation that you apply on A. But a priori, you have to do it, you do it once, you can compute this object once, but you need to compute it for each S and for each spin, right? And so it's linear, but it's kind of complicated. And so in practice, what you do is you impose it for L equal to 0 up to some L max. So this is some maximum value that you do. And you also have S, you have a bunch of grid points. That's another parameter, how many grid points you have. Okay. So that's one parameter that you have to make sure that things converge if L is big enough. The number of grid points needs to be big enough. And N, which was the number of terms in your ansatz, needs to be big enough. Right? And then you have to play with these three numbers. So a priori, if N, L, and N grid were all infinity, you should be describing all functions. But in real life, they are not infinity. They are 100 maybe. Okay, so I forgot when I started. I'm over time, but I assume that it's okay, that I should not be stressed.
Yeah.
Okay. So, okay. So, right. So this, now what I want to do here, what I will do in the next slide, I already have here a warning that the figures are coming. I want to show you the primal numerics. So, but before I show you, let me say what exactly am I going to show you? I'm going to say, what is the minimum value that we could find, this when we minimize, we ask what's the value you can have, what's the minimum value of alpha for a given N. Remember, N was related to how many terms in the unit disk you have, roughly speaking. L was when we said that we impose unitarity up to spin L. And then the other grid, the number of grid points, at how many points you impose, you can assume it's infinity because we took many, and it's more than convergent there. So this would be number of grid points. It's more than okay.
Sorry, when you're imposing your unitarity constraint, are you doing it only on the manifold S plus T plus U is equal to 0?
Yes, yes. But in fact, it's more than that. It's once you project to partial waves, you only have S, right? Each partial wave is a function of S. So you impose it at a grid in S at the boundary of the unit disk.
Okay, yeah, thank you.
For each spin. So this is what the numeric give. So this is obtained by the method I described. But before showing you that, let me emphasize that there is some not dual numerics. Dual numerics we don't have yet. It's a big open problem that I know. I actually saw that in the paper of Aninda, he said that he's working on this. So I would be very excited to learn more about it. So it doesn't come from numerics, what I'm going to say, because I don't know how to do numerics in dual. But there is an argument similar to the one I said about the holomorphic functions, that you multiply by a pole and you integrate and so on. So you can show, and I'm not going to go into the details, that alpha is proportional to the sum integral of the imaginary part of the amplitude, and therefore alpha needs to be positive. So this is an example of a dual bound. This is similar to the kind of bounds that Nima and Dubovsky and friends had shown, that some constants need to be positive because you can extract them by some contour integral, and then you blow the contour and you get, on the one hand, you get the imaginary part. As Aninda was saying, it's positive. On the other hand, you extract alpha. It's the same thing that goes into the proofs of the A theorem and so on. And so the dual argument says, let me put it in red, says that this alpha needs to be positive. Okay. And so what we exclude right now is alpha needs to be positive. So, oops. So this part here is excluded, right? So this is excluded. This is 0. And now what we are going to see is what is included by the primal, right?
Sorry to interrupt, Pedro, but just a quick question. I thought it was hard to get bounds like this in gravity because you tend to get the bound from t goes to 0, and then the t equals 0 pole sort of overwhelms the contribution from contact terms. I had thought, but you have a way of getting around this, or what I was saying was wrong.
Yeah, no, here you can, because it's in the same way that you can extract the residue of 1 over z. If you have 1 over z cubed, it's still true that if you do a small contour, you pick the 1 over z.
Okay, thank you.
So it's just that. And what's nice here is that the logs, remember I said it comes with 1 power of s more. So it's safe to do this contour. So you can really put a contour there. Because the logs come with 1 power more, this would be true in d equal 9 as well. So in d equal 9 and more, the logs are a little bit higher. So these contour integrals are really rigorous, and you can relate alpha to the imaginary part.
Okay, thank you.
And so now the question is, okay, so now we'll do primal. So we will do some numerics and we get some n. We go here, and then we increase n and we go here with some n prime bigger than n, and we try to see where can we go. Right? And this with the primal that says where can I reach? How low can I get? Knowing that I cannot for sure pass 0, 0 is excluded. Okay, so is
why is not one expecting some bound on alpha max also? I mean, something when you said alpha min here, right? Can one imagine doing the same with alpha?
Here I'm minimizing alpha. I'm saying alpha negative is excluded for sure because it's proportional to the imaginary part. And now we are going to try to see how low it is. And you're asking, do I know for sure that there is no maximum? And the answer is yes, we know, and it will become clear in a second why. Okay, I can already anticipate because in string theory, in perturbative string theory, it's infinity. So we know it cannot be, but it will become clear in a second. Okay, so is it clear what we are going to do? Because now it's a question of computer. Now the hard part is done, and now I'm going to show the plot for this. But please tell me if I want to clarify something. Otherwise, the idea is I'll show you the plots. See, they are here.
Sorry, Pedro, I didn't follow all the details. Please forgive me. But just to understand at this stage, what are the assumptions then? Are we assuming that we have a theory with gravity, this much supersymmetry, and no other massless particles other than spin 2? Is that?
Yes.
And that's it, right? No other assumptions have been made, if I'm right?
No other assumptions are being made, yeah.
Okay, thank you.
Welcome. So one more question, Pedro. So in the toy problem that you mentioned, f of 0 was easy to see. You pick a candidate f as a Taylor expansion, f of 0 was just f0, right?
Yes.
But over here, when you impose unitarity conditions, those are on the boundary, right? And if you want to now focus on alpha, you have to go to the low energy part, which will diverge because of the logs. And how do you pull out alpha from that divergent part?
Okay, so first, so the easy answer is that we don't worry because the logs are 1 power higher in S. So when you expand at low energy, you know that the behavior close to that point is just alpha. The logs diverge, but they can multiply by S. It's not like it's log S, it's S squared log S. So it's the third derivative that diverges. The function itself goes to 0 at the
I see. So the parameterization, you assume that it's just giving you alpha and nothing else.
That's right. That's what I said here. Of course, I cannot. That's where I said that in this sum, at some point, I put this. I said that we do this sum and we put this prime here to say that alpha is already out. And then this stuff starts softer than alpha. At low energy, it starts already with some power of alpha.
Yeah, okay, thank you.
Now, sometimes it's not the case. For example, we wrote a paper with Andrea and Joao recently about pions. And massless pions, the Wilson coefficient and the logs come at the same order. But that's fine because you know the coefficient of the Wilson coefficients, as Sandeep was saying. So you just subtract out the singularity and you read off whatever remains. So the logs are not the issue because we know them. They come from lower loops. So we know how things diverge there. Okay, so if it's clear, let's analyze the numerics and see what we can extract out of this numerics. So here are these numerics. Can you see? I know that the background changed from black to white, so probably now everyone's eyes is hurting. So let me explain this numeric. So here we have a bunch of curves that go and stabilize, right? They go and stabilize. right? And now let's see what this is. So this is up to which L we have. So you see that if you impose it up to spin 240, which is the most we have done so far, then it's fine. That in the sense that even if you increase n max all the way from 13 to 24, this is a lot because this is like hundreds of constants. This is hundreds of constants as well. So even if you increase from all the way from this value to this value, they reach the point where they converge, right? These points, they are converging. But if you don't impose L big enough, if you impose spin up to 140, then if your n is small, you are good. But if your n is very big, then you can fluctuate a lot because you have a Taylor expansion. And so you violate unitarity in higher spins and you are not good. So you always need to be sure that you are at L that is big enough. Okay? So how do you do in practice? Here we extrapolate and we ask, where does this curve go? And we put some error bars. And we ask, where does this curve go? And we put some error bars. And you see, it's a bit non-trivial. You have to fit. I mean, in the plot, you could say, oh, I just take the last point. And it's more or less okay. But it's much better if you fit and put some error bars. So this is what is plotted here. So here in this corner, I already extrapolated. So now I have here alpha. That still depends on n. N is going here. But L is going to infinity. Right? So we took L to infinity by extrapolating all these curves and guessing where they go. Now, it's not totally trivial. So you see that some points, if I zoom in, you see some points, can you see? That, for example, the last point has some big error bars, can you see? And okay, some points have slightly bigger error bars. That just means that when you fit, you are not totally sure where they go, here. Right, you extrapolate more or less. Now that you fit, you can go and fit now in n and guess where are these going in n. Now that you fit in L max, now you know for sure this is allowed. So this stuff here is allowed for sure. Then you improved your computer and now this is allowed. And remember that excluded is anything negative. So on the one hand, on the other hand, this is excluded. So the gap is closing. So there is still a gap. Okay, but also the way we excluded was very naive, was just based on this trivial linear constraints that Aninda mentioned. But we see that this is allowed for sure up here, and that is excluded and it's converging to some value. Now we can try to fit in n. So we take these error bars and we ask to pass by these points and fit in n. Is it clear? So that's the next slide. So then we fit here in n. So we try some power law fit and you pass by these points. And now this value where this curve here is going is this blue line. So this blue line would be the estimate for what we believe if you had enough power, the numerics would go to. And here I'm being generous, I think, with error bars to estimate that it should be something like this. So the claim is that what's allowed is 0.14 plus minus 0.06. And I really think 0.14 is probably the correct value. And so it's not 0, it's some positive value, that's for sure. And it's probably 0.14. Maybe it's 0.13, but it's probably very close to 0.14. We are now in pushing the numerics further to have more precision, but this is where we are. So finally, let me make contact with string theory. So now we ask, what is this alpha in string theory, right? So here we get that basically the picture right now is that all this is allowed up to 0.14. All this is excluded below 0. And in the middle between 0 and 0.14, there is a swamp. Okay? That's what we have right now. So there is here a swamp. This would be a swamp, and then this would be the garden, and this would be the desert. Right? And now we ask, what about string theory? And the claim is that string theory, of course, in string theory, we have a parameter, which is the string coupling. So depending on the string coupling, string theory predicts a continuous value of alpha. And the claim is that string theory is here, what you get in string theory. So in type 2b, this constant, several people like Michael Green and others studied, is given by something called some Eisenstein series. So that's alpha in type 2b. And you can see easily that this function is bounded. And the smallest it can be is 0.138 or 139. And in type 2a, it's also known, and the smallest it can be is 0.1403. And so they are remarkably very close, but this is okay, just a coincidence, it seems. But so the conclusion is that this value here that we seem to be converging is strongly coupled string theory. This would be the point at some strongly coupled point, at this point here. This is this point, this tau equal e to the I pi over 3 in this complex coupling plane. And here in type 2a, it's some strongly coupled value of the coupling where this alpha is minimum. So it is some strongly coupled value of string theory that lives right at the boundary, it seems, of what is allowed or not. So the punchline, the picture that seems to be appearing is this. So what we can say for sure is that this is allowed. These are the various primals we constructed. Then we saw, where is this converging to? If we add infinite computer power, where does it go when this n goes to infinity? And we predict it goes to 0.14 with some effort. And so the conjecture is, of course, that it goes all the way up to here, up to some 0.14. Then this is allowed. And this had to be, it could not be smaller than this because string theory nicely occupies all values from 0.14 upwards. So it seems like there is here indeed, this would here, this stuff here would be the swamp between this trivial unitarity conditions or causality of Niemann and friends that alpha cannot be negative, and this primal nonlinear formulation that seems to converge to this 0.14.
Sorry, why do you say that it takes on all possible values? Wouldn't you get a maximum for GS equal to 0?
No, when G goes to 0, you see the G equals 0 is the same as tau go to I infinity, right? So G equal infinity blows up. And here when G equal infinity, it also blows up. In perturbative string theory, this constant blows up. Right?
Oh,
it's just that you measure things in units of L string, not L Planck when you do perturbative string.
I see. Okay.
So,
I mean, you won't be able to pick out the zeta 3. I mean, in tree-level string theory, you get the zeta 3.
No, because it's zeta 3 times some ratio of L string over L Planck.
Right. Okay, thank you.
So weak coupling is here. So at weak coupling, that's why, to answer Abhijit's question, why alpha could not be bounded from above. Because above there is weakly coupled string theory here. Weakly coupled string theory. Here there is strongly coupled string theory. Strongly coupled string theory. And it seems like this bootstrap covers everything that string theory also covers and not more. Which
beautiful result.
Which sounds cute. So that's what I said. Now, if I have 5 more minutes.
I have to wait for the discussion, but it's such a beautiful result. What's special about the string theories at maximal value, 0.14? Okay, in the discussion,
yeah.
You say.
Great. So now there's something fun we can do, right? Now we can go to the boundary. And Mathematica, when we ask, it's not Mathematica. Of course, I'm saying Mathematica, but it's clusters and SDPV and so on. But so we maximize, we find the maximum, and we get the maximum, right? So now we can look at the S matrices that are there. So this is something that we don't know, right? We don't know how do the phase shifts of strongly coupled string theory look like, right? And we don't even know if these ones are the strongly coupled string theory phase shifts. They are something that has a bound. So, and the answer is we don't know yet because it's not yet converging, right? It's changing a little bit. So
sorry, could I ask, the maximum value, does that happen at G equals 1, just in string theory? Does it happen at the dual point, the S dual point?
No, it happens at this point here.
Yeah.
E to the I pi over 3.
Is this also special from the point of view of duality, of S duality somehow?
Yeah.
Probably, yeah. So here, yeah. So in type 2A, it's here, yeah.
Yeah, it's the point I think where the fundamental domain has a corner, right?
Yes, yeah, it's this corner of the fundamental domain. But is it special? Let's see. So yeah, it's probably in very.
I wanted to ask the same thing. Yeah, that is the torus, the complex structure.
Yeah, I'm plotting tau, right? Tau.
Yeah, this guy would be somehow fixed point of the Z3 action, right? I mean, there is a Z, tau going to tau over tau plus 1 or something like tau minus 1 or something like that, rather than tau going to minus 1 over tau.
That's right. So it's one of the fixed points. So we knew that if there is a minima, it needs to be at one of the fixed points, right? But we would not know which one, and it turns out that it is this one that has the minimum value.
Okay, thank you.
Okay. Yeah. So now we can ask. Okay, as I was saying, we can ask: can we see to what S matrix this converge to? And the answer is it's hard because it's not yet converging. You see, I mean, I think in a few weeks we will be able to see. I mean, we want to go, you see, n max here. If we reach n equals 30, we should be right on top of string theory. So we need a little bit more strength to push the computers a little bit more, but we are not there yet. It's converging. So I'll show you what we have. Even though it's preliminary, I believe some features are robust. So I'll tell you what we have. So what I'm going to show you now is how do the phase shifts look like when we are as close to the boundary as we can be. So now we can plot S of spin 0 of energy and ask how does it look like at the boundary.
So right? Pedro, one question. So yes. This is probably related to your comments about Stein manifolds and so on. So yes. So this solution to the primal problem, the extremal, the 0.14 solution, if you take that, then that fixes the S matrix even away from S plus T plus U equal to 0, right? Because you are. Right. So what is the meaning of that? What is the meaning of these values?
No. Sorry. It fixes. Yes, it would fix, but this is not unique, right? So there exists an extension from S plus T plus U equals 0 to a higher space. That extension is never unique because we only impose unitarity on the constraint, as Shiraz was saying. So I can always add stuff that is 0. So there is a gauge symmetry.
Right. So, yeah. Okay. So that's already there. Yeah.
So I always restrict to the constraint.
Yeah.
Okay, so let me just give you an example. For example, what happens when we increase n max and we go all the way from n max equals 17, as in this picture, to 24, which was the maximum we did. And you see, for example, this is how the spin 0 phase shift is looking like. And you see that, for example, something happens between n equal 20 and n equal 21. As the numerics are changing, you should not be scared that this looks too discontinuous because it's not. But what is happening is the following. I'll draw it with a pointer. You start with like this, and then some bump starts to appear, and then some bigger bump, and then some bigger bump. And when it's this bigger bump, you just discontinuously put this stuff here, right? But it's continuous. But what happens is that what is happening here between this point and this point when the bump starts developing and then it passes by pi over 2 at some point. What is happening is that the resonance is enter the physical sheet. So as the numerics are increasing, an unstable particle is emerging and getting into the physical street. And so this would be a particle. This is how we would measure a particle. So this would be a spin 0 resonance that is here at some units of L Planck. So at 3 L Planck, there would be some resonance here. And you could estimate its width and its location, right? So you see that it's kind of converging from here to here. It changes from here here it changes less, and then the hope is that it will change less and less. So this is probably already kind of robust. So I suspect this would say that whatever the S matrix is, for example, there should be a lightest resonance around 3m Planck for this S matrix.
So if I understood this plot correctly, the real part of the resonance, where the mass of the resonance.
The mass of the resonance is around 3, and you can estimate the width by the slope.
No, but the mass of the resonance is kind of robust even for lower ends. It's just the width that that converges only for higher ends, right?
Yes.
Okay.
But more or less, yes, in the sense you see that something is happening at that m. But I would not distinguish much between mass and width. It's all about location in the complex plane, right?
Yeah, but I can always ask.
code.
No, but I can always ask the real part. I mean, a question about the real part.
The real part of m squared, yes.
Yes,
so it looks like it's moving perpendicular to the plane, more or less.
Yes.
Okay, so how do we see this?
Sorry, Pedro, please excuse me. Just because I forgot, not fully followed. So this is, you're plotting the phase shift in 2 to 2 scattering, if I'm right?
That's right, for spin 0.
For spin
so I'm computing the spin 0 partial wave, the dominant one, at for 2 to 2 scattering, and asking, is there a spin 0 resonance or not, for example?
Got it.
That's the simplest question you could ask.
Right.
And the answer is yes, there is a spin 0 resonance around 3 L Planck square.
And no earlier than that, right? That's also
no earlier than that. Here, there is nothing.
Yeah. Okay. Thank you.
Now, how do we do it? Again, we take the amplitude that we obtained, right? So the numerics, they gives us this constant C and mk that are in the ansatz. This C and mk, by applying this linear operator for each spin and for each S, I extract the partial wave, SL, and I do it for each point here in this plot. And in this way, I plot this object here, right? So this is relatively easy to do. What I'm going to show you next is harder to do, which is to plot it in a complex plane, because I have to do it not for each S, but for S in a complex plane. But that's nicer, because then we should be able to see really this as a 0 of the S matrix. So this is what we got today. So you see that these points are wiggly, because we computed this a few days ago with many points, and I wanted to have this for the talk, so I computed this part with 400 points. So this is nothing. This is just because I wanted to show you. So it finished 1 hour ago. This is right on side. So what we see here, this is the resonance. So it's a 0. And you see what happened is that this 0 was outside the unit disk, which means it was in the second sheet, and it came into the first sheet. And now it's here. It's still moving up a little bit. It will move up, probably it will move up here or something, but not much. And then you see this value here, it's all the same color. That color is around here. It looks like 1/2, but if you convert to the right units, this means that absolute value of S equal to 1 at the boundary. So this color here is S equal to 1. And so this is the statement that here you have perfect unitarity. Here the value of the S matrix is equal to 1. We have no particle production until that point. The probability you start with 2 particles, you go to 2 particles, it's elastic. Then you reach here and you have a resonance. And you see that here, probably other resonances want to show up, but the numerics did not make it yet. Probably there will be an infinite set of resonances coming up here. But I'm not sure. And here, there are something that I don't know what this is. And maybe they are virtual states. If you plot it in the complex S-plane, remember this is rho. If you plot it in the complex S-plane, here, you see this one is very clear. This is a resonance. And then there are these ones that are almost in the imaginary direction, right? So these ones are almost in the imaginary direction. So recently there was a paper by Blas and others trying to unitarize gravity and conjecturing the existence of a gravity ball along the imaginary axis as a simple way of unitarizing gravity. So I wonder if the first guy is the gravity ball that they were conjecturing, but I'm not sure. This is super, super recent. We just found it. But it seems compatible. They were predicting something like 2/3 of L Planck, and it's exactly this value. So I don't know, but okay, this is like 10 minutes old, so I don't know. So what about for spin? This is for spin 0.
Sorry, could I ask if you go on the circle down to the left side, is that going to higher energies?
Yeah, so higher energy is here.
So it's harder to get accurate behavior for higher energies, of course.
Of course.
Yes. Okay, thank you.
Which is just what you expect, right? That high energy, I mean, the first Wilson coefficient will not be that sensitive to whether you form black holes or something, right?
Yeah. In fact, I had a question, but maybe you could postpone it to later. But there's this expectation that at very high energies, if you have fixed impact parameter, 2 to 2 scattering should be very, very small.
Yes.
I was wondering whether you could probe that expectation.
Here it is not. Here it is not. So we can discuss a bit later. Let me discuss that at the very end.
Yes, sure.
It's an excellent question. It's in the last slide. So this is for spin 0. I could also show you for spin 2. We spent all the afternoon computing spin 2, but by mistake, there was a typo in the code, so we computed spin 4. So I'm showing spin 4 instead. So we jumped spin 2. I realized that the spin 2 had some stupid typo. So this is, we are plotting here spin 4. Spin 4, you see this, there is a resonance again. It shows that some higher energy, right? It's higher compared to this, exactly as we expect. It looks like a Reggie trajectory. So there's the first one and the next one and some higher energy. And here we really see clearly the other ones trying to show up. They are more clear. And again, there are these ones that look more like some virtual states that are more imaginary, and we don't know yet what they are. Again, this is all to be taken with a grain of salt. This is what I expect, that if n goes to 100, these resonances will get in. These imaginary ones, I'm not sure what will happen to them. And what seems to be very robust, much safer than all these speculative statements, is that the first one survives. So this is the picture. So we start to see some kind of what seems to happen is that the space of theories that are compatible with 222 and only 222 seems to be very much compatible with saying there is string theory and nothing more, in the sense that string theory already covers everything. It doesn't mean that it's not a proof, because of course it could have the same alpha, but be some other theory. So it would be very nice to plot other things instead of plotting just alpha. Why don't we plot the first 2 Wilson coefficients? And then it will be really a coincidence if it's against string theory. So, and then when we go to the boundary, we see some resonances. They seem to follow a curved Reggie trajectory. Instead of a linear one, it seems to be curved with a power 3/2. But that we don't know for sure. So the conjecture would be that it is some deformation of Veneziano where the resonances all move, and it just becomes some strongly coupled version of that. But for that, we need to explore much further. So I will conclude with a cartoon. So this was the cartoon that I prepared in the beginning of the talk. So let me decorate this cartoon a little bit. So there we are. So it looks like there is this garden, and string theory goes all the way from weak coupling to the boundary of the garden where there is the swamp. And so what we are now interested in doing is, on the one hand, looking more about what we are getting here that seems to be related to strongly coupled string theory. We could repeat the same game and go to 11 dimensions and look for M theory, where it should be really an isolated point where it's not really a garden, but there should be a point, and it will be fascinating to see what we would get. And we would love to be able to, of course, have some dual arguments, because we get these bounds that are converging, but it would be great to push this desert here, right? Grab this desert here and push it and find these dual arguments that would say, yes, for sure you converge, you cannot go more, because we can improve these dual arguments and push this this desert all the way here. So as I said, I saw in this paper of Aninda that he's working on this, and I think it would be great to have some developments on this dual side. And then, as Shiraz said, we could make contact perhaps with some black hole physics at high energy, perhaps by imposing exactly the behavior that Shiraz said for amplitude, and see how that would change or come out of the numerics. But that's also the hardest part, because we are studying theories by low energy and then asking questions about high energy. So of course, that's the hardest. I'll stop here. Thank you.
Okay. Thank you very much, Pedro, for a wonderful talk. Let's all thank Pedro.
Pedro and Andrea, can I ask sort of a technical question about the kind of resources that you need? I mean, so these insanely high values of Nmax and Lmax that you considered, what kind of resources would you have needed?
Yeah, so Andrea can say much more, but right now my understanding is that each point in this, so let me just emphasize so that other people also understand a little bit. So what Aninda is asked is, before we have to compute each, here in this plot, you should remember that here there are points, right? I drew as curves, but it's points. It's for each L and each N, I compute a point here, right? So this point, each point, I believe takes 10 hours to run on the cluster. Andrea, is this correct? So I think each point is around 10 hours to compute.
So this is the PI cluster of whatever.
Yeah, we use PI's cluster and we use SDPB.
Yes,
It turns out that this problem of optimization is a linear programming problem. So you can use the same software that people use for the conformal bootstrap.
So are you using around 20 nodes at a time? Just out of curiosity, how many nodes are you using at a time? So
we parallelize. So we use all the cluster of PI, basically.
So that's a 16 node cluster, if I remember correctly, or is it even more powerful now?
I don't know, but if you go to the queue, you just see Andrea, like total takeover. So.
I see.
Hi, let me say just something quick about the
yes,
cluster.
Yes, Andrea, yes.
Right. So with the parallel version of SDPB, we can use like the single node that PI has like 40 cores.
Yes.
So with 40 cores, we can easily do Nmax 22 and Lmax around 200. And it would take like 7 hours.
I see.
Let's say. Then for the last Nmax, we push to 2 nodes, let's say, and it scales pretty well. So each of these runs can take from 10 minutes for Nmax equal 13, and for the biggest Nmax and Lmax, it would take over 10 hours. Of course, if we could increase the number of nodes, it would take less time. But for now, this is the scale, let's say.
And what is the precision that you're using? Is it like 1000-digit precision?
Yeah, we are using like 1000 binary digit precision.
Okay.
And we checked, I made some preliminary checks, and you can lower it or increase it a little bit, and the results are, they don't change.
Okay, thank you.
Yeah, just so that people, just a comment that since we are saying that we have stellar expansion in these disks, right? So it's obvious that you need a lot of precision, right? You have polynomial expansion. If you go to degree 40, right? A small mistake immediately changes the value at higher energy or something, right? So in practice, you need to compute this linear operation. You don't do it numerically, for example, to compute this because you have to do it analytically and store files and so on. And then it's fun that all the operations you do is like multiply matrices, and it's stuff that is analytic. But you start with like 1000-digit precision, such that even multiplying things, you lose a little bit of precision in the computer. And at the end, you want to get 300 digits. You have to start with 1000 digits so that Mathematica multiplying matrices at the end ends up with 300-digit precision. Right. And then those 300-digit precision you feed into SDPB, and SDPB produces this alpha minimum that then we feed to extrapolate to infinity.
Yes, thank you. And Pedro, just I wanted to take your as a this. Do you think that this could ever be possible to do it on a laptop?
Oh, but yes, I think so. Yeah, I mean, there are always clever things that we can. So this is the simplest thing, which is we just impose unitarity spin by spin. But there probably are some averaged quantities that you. So for example, I'm oversimplifying a bit, but we also said instead of imposing up to spin 240, why don't we estimate analytically the large spin behavior and impose that? And we also did it. Okay. And we can estimate analytically the large energy and impose that. And but those things, maybe with imposing some clever asymptotics, immediately makes this convergence instead of going to spin 200 to spin 40. Right. And then you can do it on a laptop.
Right. Another related question is that this high energy behavior. So usually, did you make any assumptions about the high energy behavior? Because the row variables give you a particular high energy behavior. It's a constant at large values of energy, right?
Yeah. So we just impose that it's smaller than what we know axiomatically must be. So we are very generous with large energy.
Right.
So a priori, the ansatz, if you're not careful, the ansatz naively diverges a lot because it comes with this extra s to the 4 in front. Then when you compute partial waves in 10 dimensions, there is an extra s cubed.
Yeah.
So if you don't naively, the partial wave, if you compute the partial wave that comes from decomposing the ansatz that we have, it grows with s to the 7 at large energy. But it needs to be smaller than 1 in absolute value by unitarity, right?
Yes.
So we allow much more than what we need, right? So a priori, it needs to go to a constant because it's a probability. But the ansatz is such that it could even grow as s to the 7. So it can behave as whatever it wants, and then it eventually goes to a constant as it must.
So are you saying that you would be able to probe things like the Frossard bound or the Gin-Martin bound using these kind of numerics? I was under the impression that you cannot.
Probably not. I don't think so. So let me mention, yeah, I can say something that there is a puzzle in general in the S-matrix bootstrap that is not common to this problem. It's common to all problems, which is that at the boundary, we seem to always, in the end, if the numerics are good enough, they converge to things that are either elastic or almost elastic. They almost never produce particles. Mm-hmm. So in 2-dimension, it's fine. Integrable theories don't produce particles, and maybe they are the boundary of the space of theories. But in higher dimensions, there are theorems that say that you cannot not produce particles. You must produce particles.
Yeah, this is the Axe theorem. Yeah, this is the Axe theorem. Yeah.
This Axe theorem says, if you are at high energy, you must produce particles. Mm-hmm. But it's a mathematician's theorem. It says you must produce. It doesn't say how much. It doesn't say, can it be 10 to the minus 120? Yeah, maybe. So it just says it cannot be 0. Because if it's 0, analytic continuation of 0 is 0. So the argument goes, if something is 0 here, then by analytic continuation is 0 somewhere there, and eventually you reach a contradiction. But analytic continuations of things very small can become very big. So, okay, it cannot be 0, 0, but maybe it can be very small. But there is this tension that it seems like at the boundary of the space of theories, typically you saturate unitarity. So you see that the color is always the same. It's not the same here where you have the resonance, but that's just because the numerics didn't converge yet. As the resonant enters a little bit, it will be just a ball surrounded by the same color again. And that's fine. That just means that this S-matrix tends to saturate things that saturate unitarity within the subspace of external states you consider. So we studied 2, 2, 2, so we saturate unitarity in 2, 2, 2. If you did 2, 2, 4, it would saturate unitarity in that subsector. And it would converge to the optimal S-matrix only when you converge towards all possible states as external states. So that seems to be the mechanism. Now, if that's the mechanism, then it would mean two things. It would mean that on the one hand, we don't expect black holes to show up automatically because black holes produce particles, right? It's precisely the probability goes to 0 instead of going to 1. But on the other hand, we found strongly coupled field string theory, or at least the same constant at low energy. So that just means that high energy is not changing this alpha coefficient, which is fine. I mean, it's intuitive. The first irrelevant operator doesn't receive contributions from infinite energy. Okay, that's fine. But on the other hand, it will be very interesting then if it doesn't come out automatically, but if we know it's there, that's what I drew in the last cartoon, it would be nice to impose this behavior. If it doesn't come out automatically, we could impose this scaling, like Shiraz was saying. As S scales with L square and both are big, there is this black disk picture that you cannot have a particle, you must have 0 exponentially small amplitude there. So we could impose it and see what it would change. I think it will not change alpha, but by imposing that the amplitude is very small in some region here, it will definitely move the resonances in the complex plane. And what it will do and so on will be interesting to investigate. But that's step 2. Step 1 is really see where things converge to.
But Pedro,
I have a question, please.
Oh, go ahead.
Sorry.
No, please go ahead.
No, sorry. The question is the following. See, a strongly coupled string theory, even at low energies, has a black hole solution, right? So this 2 to 2 S matrix that you start with, the initial ansatz for like 1 upon STU, etc., that won't be valid, right?
So at very high energy, no, that's a low energy expansion, what I wrote. That's why I wrote low energy.
But what I'm saying is that the black holes are low energy configurations in slowly varying fields. I mean, it is true that high energy collisions produces black holes, but if you look at Einstein's theory, at low energies, at long wavelengths also have a black hole solution, which is asymptotically flat, etc.
It's two different things. So one thing is to say I'm in flat space and I scatter a graviton against each other, and then I can form a black hole, and because of that, the probability at very large energy must be very small.
That's right. But I am
So
asking for
that's
the other
only-
problem actually, where I need not. When you talk of only low energies, I do have black hole solutions as strong coupling. I'm just wondering whether that's a different problem that you will try to address.
Right. So one thing is saying in 222 of gravitons,
Yes.
there is some high energy region where I have black
Yeah.
holes. So that's one
Absolutely.
thing. Another thing is to say, another thing is to say, I can consider a black hole as a background, and on top
Yes.
of this background, scatter particles even at low energy, right?
Yes. Yes.
That's a
yes.
different problem. That's like scattering two gravitons in the presence of a black hole. That's much harder, of course. That,
No, I mean,
or at least
it's a,
harder, right?
no, certainly it is a harder problem, but it's a physics problem in the sense that the stuff is there, whether you like it or not, at low energies. So is it a different sector, or can we sort of distinguish between?
No, I mean, but if you think from a particle physics that you only have S matrix, what you are describing is more like you have two particles scattering plus many other particles that form the black hole, right?
Yes, yes.
And then in the future, you have many particles that form the black hole. And now, okay, what do you have? It depends if the particles fall or not, but maybe you have 4 particles here outside. So this is an example of an amplitude, right? That's one thing you can have. And this amplitude, then you could compute it in some background approximation that these fields almost don't move and so on. That's one thing.
Right.
Another thing is, no, in the initial state, I just have 2 gravitons that I can also do, right? I don't have any black hole. But still, in the future, I could produce a black hole.
Yes,
and
okay,
therefore, the probability of going to 2 particles would be exponentially small.
Right.
So it's different. Right? It's 2 different things conceptually.
I agree. I understand. So there are different calculations you can do. Okay,
yeah.
fine.
So this one, black holes show up at high energy, right?
Yes, that's right. Yeah.
And whereas here, the black hole is there, as you say. It's a low energy solution. Things change slowly and so on. And
that's right.
And here it can be. It's at any energy. The black hole is there.
That's right. Okay. Thanks. Thank you.
So Pedro, to come back to your right side picture where the black holes are showing up at high energy, I was little puzzled by your comment that we may want to impose the kind of exponential softening that black holes would lead us to expect, as Shiraz was saying. Because isn't that something that must come out of any consistent theory of gravity, you might think, because black holes should form? I mean, if we have to impose it, that might suggest you have consistent S matrices in a theory of gravity without black holes. I mean, that seems very puzzling, no? I mean,
yeah, that's true. That's true. On the other hand, even more basic than that is the statement that I said, that we are finding solutions that are elastic to very high precision. And even in quantum field theory, that's strange. And that's even more basic. And there doesn't seem to be anything particularly wrong. They are not exactly elastic. They have particle production, but it's very little. Yeah, I don't know.
I was wondering, at least in a theory of gravity, could it be that this behavior that the boundary is elastic changes if you go to sufficiently high L? I don't know. Because if you form a black, I don't know. No, I don't have a good idea. No, I'm not sure.
So you are right. So a black hole you would see at fixed impact parameter, right?
Yeah.
Which means that which is like S over L squared, basically, right? So it's large energy, large spin, such that you have some macroscopic impact parameter.
Yeah.
So you would scale both S and L and see how the partial wave at fixed S over L squared at fixed impact parameter, at some point there is a black hole.
I see.
Yeah, I don't know. So there is a further thing. So we have this problem and we have these points converging to something, and we don't have a dual problem. Okay, so I know that Andrea is thinking about it. I know that Aninda is also thinking about it. Some people are thinking about it. It would be great to have a dual problem coming from the other direction. Now, when you have dual problems and primal problems, often you can show that the gap needs to close. That it's often the case. If the problems are convex and there are some simple conditions under which the gap needs to close. Okay. In 2 dimensions, that argument implies that you really cannot have particle production. because you can easily see that for the gap to close, you cannot have particle production. Nice. It's actually very simple to see from the holomorphic function example I gave you. Let's go there. So you see that the bound is saturated when this guy here is 1, right? Mm. If you remember this. And this is like particle production. It's when absolute value of F is equal to 1. Nice. Right? That's when you saturate the bound. Nice. So in this problem, to saturate the bound, it's not like F is smaller than 1, it's equal to 1 in absolute value. Then you saturate the bound. And this is the type of problem that if people that know these optimization problems could tell you right away, that if there is a dual, the gap is 0. Nice. And so here, these amplitudes are like one holomorphic function because they only have energy in 2 dimensions, so they cannot produce particles. Just that follows from the existence of this dual formulation. There should be some caveat in the higher dimensional version, or the higher dimensional version of the dual problem should not imply so easily absence of particle production. The naive versions you would write would imply 0 particle production, but then they would contradict this Axe theorem. But it can be about uniform convergence versus total convergence, and again about this order of limits of analytic continuation of a small quantity can be a big quantity and so on. So there are several puzzles about that that I think are very interesting, and in particular in theories of gravity and at high energy, they make contact with fancy things like black holes and so on. But even in regular theories of pions, we produce kaons, and we don't need to go to black holes to want particle production.
Thank you. Thank you very much for a beautiful talk. Thank you.
Thank you.
Hi, Pedro. I had a quick question. Actually, this is a question that Abhijit constantly asks us in our discussions. But since he's not asked it, I will. The basic physics that you imposed is that this partial wave amplitude cannot have modulus greater than 1. Now, suppose you looked at this problem, you put this problem in ADS and maybe made the ADS very large. So you went to the flat space limit. Yeah. This problem that you had would then have a dual conformal bootstrap version. And I wanted to understand where in the conformal bootstrap what is the conformal bootstrap version of the statement that SL cannot be greater than 1? What conformal field theory physics is that?
Yeah, that's an excellent question. So as you are pointing out, you can put it in ADS. Then, as I was describing here, this condition that it's smaller than 1, you can think that it's a stronger condition than being in the upper half plane. So being in the upper half plane is the analog of C² positive in the 3-point function of the bootstrap, right? It's up here. But being inside the circle, as you point out, it's stronger. Now, there are many ways of taking the flat space limit. And then after you take the flat space limit and take ADS to be very large, of extracting these phase shifts. In one of our paper with Joao and Balt and Miguel Paulos and John Toledo and Balt, we proposed one way of extracting these phase shifts. And in that way that you construct by constructing some wave packets and taking ADS to be very big, these phase shifts are mapped to averages of exponential of phase shifts of anomalous dimensions. And just because they are averages of phases, it looks like it's automatic that they are inside this circle. I don't think it's totally satisfactory. It assumes that some generalized free field theory, asymptotics for 3-point function is true in any theory, basically, in this proof. In 2 dimensions, okay, what I want to say is that I think in 2 dimensions, together with some papers of Dali, Mill, and so on, we could probably see this absolute value of S smaller than 1, even in the CFT. But I think in higher dimensions, we don't know. I think in higher dimensions, this condition of unitarity, the upper boundness, even the upper boundness, just saying it's smaller than this value, right? I don't think we know what it translates to in the CFT.
But you expect it to be a theorem you can prove that follows in the end just from allCijk squares being positive?
Yeah, I think it will follow from all the C squares being positive, and then it will follow that there will be a next statement that the phase shifts are related to averages with positive coefficients of phases, and that will give some estimate for how big it can be. But one more important step will be that I think it will also assume something about the exponential decay of this 3-point function as the dimensions are very large to have some universal behavior to be that of the generalized free field. So it's like in these proofs of, often it's the case that in some limits, right, everything has to behave like generalized free boson because particles are very separated, for example, or something like large spin and so on. So it's often the case that sometimes you get some universality of 3-point functions. And it seems like there should be some kind of universality of the 3-point functions. That I think we could not prove. If I remember correctly, it was already a few years ago, but I think that was an assumption. We had to assume something about the asymptotic growth of the 3-point function.
But so this is S matrix bootstrap QFT in ADS paper?
Yeah.
But in principle, even that other thing about behaving like a free field should in the end just follow from Cij squares being positive. What I'm trying to understand is there's no new physics, right? Apart from that, that should imply everything in conformal field theory or not?
I believe so. Yeah, that's what I believe. Yeah.
Thank you.
But I don't know how to prove it. It's just I would believe that, but I cannot prove it.
Thank you.
But this thing that is a manifest consequence of unitarity in the bulk somehow has a kind of a subtle consequence in CFT. That is what is a bit difficult to reconcile. But maybe I don't know. Maybe it's fine. Yeah.
No, in general, I think ADS is amazing that you just have the axiomatics of CFT and somehow it knows about the S matrix bootstrap. I find it spectacular. You see, there are here the analytic properties were simple, but when you deal with particles, with a heavy particle, if you scatter heavy particles in a theory that has lighter particles, the analytic properties of amplitudes are super complicated. It's really a huge beast. If you have even if you have 2 particles, M1 and M2, and if you scatter the heaviest one, and in intermediate steps you have the lightest one, the analytic properties are much more complicated than what I described. And somehow the CFT should know about this and should be like a black box that gives you the right result and knows about all these Landau singularities and all this analytic structure of amplitudes that we don't know.
Okay. Thank you.
Maybe it's a little analogous to the way that some things can be got out of causality very easily. And causality follows from reflection positivity, but it's harder to get these things out of reflection positivity. A little like the results of Hartmann and friends.
Right. So reflection positivity is more like this statement. It's this being positive here.
And reflection positivity implies causality, but it's often easier to get useful things out of causality than starting with the reflection positivity.
I see.
Okay. Any more questions? I guess it's quite late for Pedro over there.
Nah, for me it's okay. Don't worry.
Okay. If there are no further questions, let's thank Pedro again for a wonderful talk and being so patient with all the questions.
No, thank you. It was